morning to all. Myself Professor Archana. We are continuing on topic fundamental of a carbon capture, utilization and storage. In today's discussion, I am going to talk about ternary phase diagrams in CO2 EOR flooding. So let's start with it. So we have get the idea of CO2 EOR flooding. So what we do in CO2 EOR, it does involve injecting carbon dioxide into oil reservoir, and it does improve the oil recovery. How? By oil swelling, viscosity reduction, interfacial tension reduction, and that often this injected CO2 acts as a solvent that becomes miscible with oil and under certain conditions. So in today discussion, we are going to talk about the ternary phase behavior, usually in water, oil or CO2, which is crucial for understanding how these components, that means oil, water and CO2, interact and distribute themselves, affecting your recovery efficiency, especially in miscible and immiscible scenario. So we have to talk about the two type of a CO2 flooding mechanism, that is a miscible CO2 flooding and immiscible CO2 flooding. So when we mention ternary diagram, so ternary diagram for CO2 EOR commonly it will illustrate a CO2 water oil system is a triangular plot. So the plot would be something like that. So this is the plot we are talking about. It would be like this. Then it would be like this. And then we do have a like this. This is the triangular plot we are talking about, where on the vertex you will have A, B and C. So a ternary diagram for CO2 EOR, normally it does illustrate CO2 water oil system, and it is a triangular plot as the plot shown by this one, and that represent all possible mixture of these three components. So the three components which we are talking about, vortex 1 or A, that is your water brine, so it may have this, we can write H2O. Then talking vortex 2, oil, so this is hydrocarbon, and then vortex 3, that is a CO2, so this is the injected gas. So then we do have the vortex ABC, which is getting represented by the three component, water, oil and CO2. Then there are area inside the triangle that does depicts different phase behavior depending on the pressure and temperature of the reservoir. So this ternary diagram for CO2 EOR, we have seen that one, and it does has a multi phase equilibria to determine the solubility phase behavior and then compositional changes during your miscible and immiscible displacement process. So what is the key feature we have seen it? Then here there are a vertex component and the three corner representing the pure component. These three vertex A, B and C, it is a representing the pure component. And then we do have the phase region. So this diagram define areas of the single phase, two phase and three phase flow, and then where it will be applied, it is used to analyze phase behavior, which we call solubility in your water and oil, and to optimize the mixing ratio for your EOR. So component behavior, CO2 often acts as a solvent and that does reduce the oil viscosity, while water is used to control the mobility. So we do have the CO2 which is acting as a solvent, and this solvent will reduce this oil viscosity. And then other component we do have a water which is used to control the mobility. So under typical reservoir condition, CO2 is injected into a system, and that system, that the porous media, is often already filled with oil and Contd water saturation. So this ternary diagram explains how these phases interact. So we have the two-phase region. So two-phase region. So this two-phase region will be liquid-liquid or liquid-vapor. So within this zone, two phases exist. So this two phase, that means CO2 rich phase and oil rich phase. In immiscible flooding, so this zone is prominent, and the separation between your CO2 and oil means a lower recovery efficiency. When we do have the single phase region, that is the phenomena of a miscible flooding. So in this region, CO2 and oil are fully soluble in each other and that form a single phase. So this is the ideal scenario for maximum oil recovery. Then we do have the three-phase region. So that's the three-phase region, liquid vapor. A region where water, CO2 and oil exist or coexist in a equilibrium. That exists in a equilibrium. So then we do have the tie line. So these are the lines connecting the composition of the two phases in equilibrium. So two phase we do talk oil rich phase and gas rich phase. Then the slope of your tie line dictates the partitioning of your component between oil and water. So we can see it here, one typical ternary phase diagram for system of component A, B and C, and it is having the limited visibility. So this is A, B and C. Then we do have the one phase region and we do have the two phase region, and then we are talking about the two phase composition. Then we do have the different point. We are talking about the critical point, and then we do have the tie line. So let's talk about detailed ternary mechanism in CO2 EOR. So we have this miscible flooding. So miscible flooding condition is at the high pressure. So as pressure exceed your minimum miscibility pressure, so pressure is greater than mmp. So this is my first scenario. So this two-phase boundary shrinks and the tie line disappears. So here we are talking, this is the two-phase region or two-phase envelope. So this the two-phase region shrinks. That means there is a tie line. So this tie line will get it disappear. So in miscible flooding, as the pressure exceeds the minimum miscibility, the two-phase boundary shrinks and the tie line disappears, and that allows the system to enter a single-phase region. And in single-phase region, what will happen? The interface between your oil and CO2 will vanishes, and then sweep efficiency increases significantly. So here IFT will become 0. Then the second one, we do have the immiscible flooding. So this is at the low pressure. So when pressure is less than mmp, minimum miscibility pressure, two distinct phases, that is liquid and gas, exist, but CO2 is still dissolved into your oil, and that causes oil swelling, lower viscosity and reduces the IFT. Then we do have the another ternary mechanism in EOR in case of water alternating gas processes. So this process is often plotted on a ternary diagram to show the trajectory of a system between your water rich and CO2 rich areas, and that optimizing the sweep efficiency. Then another one, we do have the carbonated water injection, CWI. When water pre-equilibrated with CO2 is injected, the ternary diagram shows the migration of the system towards your oil rich zone with CO2 partitioning from water into the oil. What are the different operating conditions? So this operating condition is a pressure. So higher pressure moves the system towards your single phase region, because at the miscible flooding, what we have seen at high pressure, this high pressure, as the pressure exceed your minimum miscibility, the two phase boundary shrinks, and then tie line does get it disappear, and that allows system to enter into your single phase region. So as the single phase region, there is no interface between your CO2 and oil, and then you do have the more sweep efficiency increase in this case and more recovery. So the first impacting criteria of operating condition, that is the pressure. So higher pressure moves the system towards your single phase region, and that lower the IFT and it does increase the miscibility. Then second, we do have the temperature. Higher temperature typically requires the higher pressure, that means higher mmp for your miscibility. Then talking about the composition, light oils are more miscible with CO2 at lower pressure, while heavy oils requires the higher pressure. So these are the impact of a operating condition. So we are talking about the miscibility, miscible CO2 injection, immiscible CO2 injection. So what understanding we do have about the miscibility? What is miscibility? So miscibility is a mixture of the two fluids. One fluid dissolve a second fluid either at a first contact or multiple contact consecutive stages, as the injected fluid or injectant fluid, that is your CO2, contact and displace the second fluid. So the second fluid we are talking about the oil. So there is a two type of miscibility in CO2 EOR that we have seen. So there is a first contact miscibility and multiple contact miscibility. So first contact miscibility is driven by fluids composition and the thermodynamic condition. So that thermodynamic condition, we have the pressure and temperature condition. An important feature of miscible gas injection displacement is the solubility effect of the gas displacing the miscible oil, which eliminates the gas oil relative permeability effect, which is the consequence of the dissolution of the displacing fluid into displaced fluid. So that converts your displacement as one uniform front moving at the interface of the gas displacing oil. So this is the scenario of your miscible gas injection. So here there is a diagram shown. So CO2 injection miscible displacement in a porous scale. So there is a, we do have the injected CO2 and that encountered the trap oil. Then here CO2 and oil mixes, and here finally there is a mixing takes place. Oil expand and move towards your production rate. So this figure below shows gas, that is the CO2 miscible displacement of the trapped oil in a porous medium. So this CO2 gas mixed with oil swell the oil molecule, extract light component from the oil as it moves into your reservoir, and that create a visible virtual wash of the porous medium. Other characteristic of a miscible gas displacement. A miscible gas displacement can remove and displace the trapped oil in a porous which is not movable by your immiscible displacement. So miscible displacement can be achieved by injecting the gases. So the gas injection we have taken it CO2. So other gases can be also injected. So this injecting lean gas, then wet gas, and C1, C2 and CO2, etc. So at minimum miscibility pressure, the interfacial tension between your oil and displacing fluid is approaching zero. So this is the scenario of your miscible displacement. So in miscible displacement, there is a oil swelling, viscosity reduction, formation of a single phase. But in case of immiscible, there is a, compared to miscible, there is a less recovery, but you do have again the oil swelling will take place and then viscosity reduction will be there. So this is about it. So under normal condition, what is happening? Oil and gas reservoir fluid form distinct immiscible phases. So the immiscible phases are separated by an interface associated with your interfacial tension. So when the interfacial tension is equal to 0, the two fluid mix achieving your miscible condition. So this residual oil saturation to gas or water is directly proportional to your interfacial tension IFT. So miscible displacement is characterized by your low or zero residual oil saturation. So the two processes we have seen in miscible and immiscible. Under that miscible processes, we do have the two type of miscible process or mechanism. So that the first one is the first contact, and then we do have the multiple contact. So there are two basic type of miscibility. First contact occurs when the injectant dissolves the oil as soon as it gets in contact with the reservoir. So it usually occurs with solvents such as your gasoline and very rich gases. Then another miscible process we have here, multiple contact miscibility. A multiple contact miscibility starts as an immiscible displacement. Then the thermodynamic condition, that is your pressure and temperature, allows a continuous transfer of a molecules of a hydrocarbon from the displaced oil to the injectant, that is your displacing phase. So this injectant is here clean gases and others, so CO2, in a condensing and vaporizing process. So there is a two process we have talked about, that is a condensing and vaporizing, that does enrich continuously the injectant gas until it becomes miscible with your displaced oil. So initially multiple contact miscibility starts as an immiscible displacement, but as the time proceeds and at the given thermodynamic condition, that is the pressure and temperature, finally it achieves the miscibility. So the mechanic of miscibility injecting a dry gas is defined as a vaporizing drive, and it is controlled by the oil composition, pressure and temperature. So this miscibility achieved through your multiple contact between injection gas and the oil in place occurs after the injection gas at the displacement front progressively contact the oil in the reservoir. So as the displacement front moves into the reservoir, the gas takes more heavier component until the miscibility is achieved. So in presence of your viscous fingering or permeability heterogeneity, the minimum distance to accomplish the miscibility increases because of the dispersion at the displacement front. So this is another important thing. So how this miscibility, multiple miscibility does get it affected? Due to the presence of your viscous fingering or permeability heterogeneity. So this here we do have the phase diagram. In a phase diagram, which is shown it here, the first contact miscibility pressure usually occurs at above the bubble point pressure. So that is a condition of the first contact miscibility. So in the first contact miscibility, if it's shown on your phase diagram, so this first contact miscibility usually occurs above your bubble point pressure. So the Cry-Condon is the maximum pressure. So here we do have the Cry-Condon bar and then we do have the Cry-Condon, and here we are talking about this is the Cry-Condon, this is your Cry-Condon bar, and then here we do have the another point, that is your critical point. Then we do have the different dew point line, then we do have the dew point line, then we do have the different bubble point line, and this is the pressure temperature, and this is nothing but the phase diagram. So here Cry-Condon bar is the maximum pressure here, that gas phase cannot be formed anymore regardless of its temperature. So its temperature is called Cry-Condon bar temperature. So Cry-Condon is the nothing is the maximum temperature that the liquid cannot be formed regardless of the pressure, and its pressure is called the Cry-Condon pressure. So this is the definition. So at temperature higher than the Cry-Condon only one phase occurs at any pressure, and the corresponding pressure we call the Cry-Condon bar, that is the maximum pressure above which no gas can be formed regardless of the temperature. So the temperature pressure phase diagram for an oil system illustrates the position of the Cry-Condon bar pressure, the bubble point line, and the two phases liquid and gas envelope. So the area above the bubble point line and below the Cry-Condon bar pressure define the region where the multiple contact miscibility might take place. So here we are, this the area we are talking about. Under this there is a multiple contact miscibility will be there, and for the first contact miscibility usually the pressure above your bubble point pressure. So here we are talking about the ternary diagram. So normally ternary diagram are used to represent the phase behavior of the hydrocarbon system. So just now we have seen the normal phase diagram for the system. So this ternary diagram are used to represent the phase diagram of the hydrocarbon system. So the mixture of a component of the fluids with more than 3 components divided into 3 pseudo components, such as a light, intermediate and heavy component of a hydrocarbon phase. So this ternary diagram are developed based on a compositional equation of a state EOS developed to replicate the phase behavior of your hydrocarbon system, and that are useful to represent the phase behavior of the mixture of the pure component also. So this composition of the 3 points in the ternary diagram is defined based on your oil composition and the injection fluid composition and your water. So this thermodynamic criteria define the minimum miscibility pressure, that is a MMP in a ternary diagram, as the pressure above which the limiting tie line passes through the point representing your oil composition. So the tie line in a ternary diagram represents the two fluid being mixed, and two fluid being mixed, compositional concentration of the two mixed fluid are given by your end of the tie lines. So the mixture composition lies on your line. Its position depends on your concentration ratio of the two end point fluids. So we do have one example which is shown by this diagram. So what it is all about. As for example, in figure given, a gas composition 50% C1, that is a methane, 50% C2 to C4 will lie in the midpoint of the C1 and C2 C4 corner. If I have to find it out, a gas composition 50% C1 and 50% C2 to C4, so that will lie in the midpoint of the C1 and C2 to C4 corner. So here this is the C1 and here we are talking about C1 to C4. So this is the, we do have the midpoint where we are talking about the, it will lie to 50%. So for this composition, we do have a blue area, that is the one here we are showing. Blue area correspond to the mixture that result in two phases, that is oil and gas. So now this one, this miscibility occurs when a gas composition gets in contact with your oil composition without crossing the two-phase area. So where the miscibility occurs? When your gas composition gets in contact with the oil composition without crossing your two-phase area. So this is the one which we are talking about. So we do have the green line which just for example, what it represent for? It does represent for your gas composition 50% C1 and 50% C2 to C4 will lie in the midpoint of the C1 and C2 to C4 corner. Now here that we are talking about, a green area represents the mixture of the three groups C1, C2 to C4 and C7 plus resulting in your two phases gas and liquid. So we do have a triangular diagram that is given by this one, this representation, and with C1 at the top corner, that we can see C1, or we can call this the C1 because this is a pseudo diagram here. Then we do have a C2 to C4 at the bottom right and C7 plus at the left corner. So C2 to C4, that's the one, C6 it is written here, C2 to C4 to the right side and then C7 plus we do have it here. Now here we were understanding the multiple contact and your first contact miscibility. So on the phase diagram or ternary phase diagram, a multiple contact miscible process MMP with dry gas is illustrated in 4 steps in a phase diagram in figure next. That's the one, multiple contact miscibility with your 4 steps. So let's understand this. So here it is a multiple contact miscible process MMP with dry gas is illustrated in a 4 step. So this injection gas is composed of by pure C1. It is represented with the point G in the diagram. So where it is, we do have a G in the diagram. So here we do, this is the injection gas we are talking about. So the injection gas is composed by pure C1. It is represented with the point G in the diagram. As the C1 gas moves in the reservoir, what will happen? Thermodynamic interaction. So here the injection gas is C1, that means we are injecting the lighter gas. So when in CO2 flooding, we can have the different type of gases can be injected. CO2, then wet gas, then we can inject C1. So here it is taken the injection gas as a C1. So as the C1 gas is being injected and that is being represented by the value G. So this is G is nothing but the injection gas. So let's see this one. As C1 gas moves in the reservoir, what is happening? Thermodynamic interaction with the oil component occurs, makes the C1 extract the intermediate components such as what it is extracting C1 to C4 from the contacted oil phase. So this is my first phenomena. First there is injection of a gas and that injection of a gas is nothing but a C1. So as the C1 will get it injected, it will move this gas in the reservoir. Then there would be thermodynamic interaction with the oil component and that makes the C1 extract the intermediate component. That the intermediate component we are taking C2 to C4 and as it contacts the oil, it extracts this component from the contacted oil phase. The second step we do have, as the gas move forward, This intermediate molecule weight hydrocarbon from the injected gas will be transferred into your oil phase in the reservoir. So this is my second phenomena. As the gas moves forward, the intermediate molecule weight hydrocarbon from your injected gas will be getting transferred back into your oil in the reservoir. Then, because of the phase transfer mechanism, some of the gas will condense into your oil during this process. And the fourth step we do have, the reservoir oil now will becomes enriched with these material which is condensed back into the reservoir until this miscibility occurs between the injection gas that has already extracted your higher molecular weight component from the residual oil and the enriched oil at the displacement front. So this is the fourth step will occur. So first there is a gas injection, then intermediate component will be getting transferred from the oil to your gas, then gases will be enriched with intermediate component and then again it will go back into the oil phase, and during that time some of the gases injected gas will also will get into the oil, and then this will keep happening until there is a final single. Multiple contact will be there, multiple time it will occur, multiple miscibility will be there, and then you will have the single. Then we do have the plate point is a critical point at which the liquid and vapor phases are identical. So which is the plate point? This is the one, the plate point, and this plate point is the critical point here. So this plate point is the critical point at which liquid and vapor phases are identical, and then miscibility occurrence is a function of the solvent concentration, and then injectant composed by pure C4 and high C4 concentration achieve first contact miscibility. If we do have the injectant and that is composed of your methane and high C4 concentration will achieve your first contact miscibility. But here when we are injecting the lighter component C1, we have the multiple contact miscibility. As the proportion of the solvent C4 reduces, there will be composition where there is a no first contact miscibility. That means we are mentioning when there is a lighter component injection, so there is a no first contact miscibility, and the miscibility might occur by the multiple contact. Then as the C4 proportion reduces, the miscibility is lower until a point where there is no miscibility at all, and that we are showing in the next figure. So this is the figure we are talking about. So here gas composition with no miscibility, then we do have gas composition with the multiple miscibility, then line, let's understand this. So here we are talking about the condensing gas mechanism sequence. So reservoir pressure is lower than the MMP. So when this will be, when we do have the reservoir pressure is lower than your MMP. So this solvent or your injectant and the oil are not miscible initially. And as the dry gas moves in the reservoir, there is a transfer of a hydrocarbon component from the residual oil to the injectant and from the solvent component transfer to liquid oil phase. So there is a first transfer from oil to gas and then from the solvent component transfer to the liquid oil phase. So this repeated contact between your oil and solvent moves system towards your plate, or that is the critical point, and that we call the dynamic miscibility will be there. So as the pressure increases, this two-phase region becomes smaller. At some pressure, the injectant gas is to the right of the limiting tie line, and then you will have the MCM developed, or multiple contact miscibility developed. So this process we call that condensing, vaporizing, multiple contact miscible drive. In case of your vaporizing gas mechanism, intermediate component, hydrocarbon component in the oil phase vaporize to enrich the gas, and as the trailing edge of the gas slug becomes sufficiently enriched, it becomes miscible with your reservoir oil. So this is the process, and this was shown on this diagram. So let's move towards your challenges in your miscible gas injection project. So one difficulty in miscible gas displacement project is to keep all the reservoir porous media above your minimum displacement pressure. So several pressure level can coexist in your reservoir because of your pressure gradient and the flow dynamics in your heterogeneous reservoir. As your sedimentary environment composed typically by river channel, plain sandstone bars, and etc. And in carbonate reservoir with several phases within the reservoir unit. So if there is not a well-defined safety margin above your MMP, there might be areas with a pressure below the minimum miscibility pressure you might occur. So when the pressure is below minimum miscibility pressure, that time we have the immiscible displacement. So it is a common to receive management requirement to produce at maximum potential with which might not correspond to your injection rate designed to maintain the reservoir pressure. So we do have the requirement to maintain the reservoir pressure above the MMP. So this is a challenge in MMP project that might cause detrimental effect to your recovery factor. So this is one challenge we do have. Then in the last decade of a past century and early times of this century, the oil and gas operator realized that importance of understanding the fluid phase behavior and its characterization with application of a fluid phase envelope, and it is used as a reservoir management tool. So that's the importance of this one, understanding this fluid phase behavior. And in many cases, the feasibility to increase dramatically the recovery factor are recognized after understanding the reservoir dynamics. In some cases, a late implementation of an MMP EOR project was hampered by the high cost of depressurizing the reservoir at level that would be adequate for MMP displacement. So this type of issue has avoided a more extended implementation of a EOR miscible gas injection project. And then another problem, gravity stable injection of a gases into your high relief oil reservoir can result in substantial increment oil recovery, and that depending on your density of the gases at reservoir conditions. So the gases should be injected at crest of your or bottom of the reservoir, while your miscible displacement can be in low reef or flat reservoir. So that's the thing. So viscous fingering is another challenge that can result in your poor vertical and horizontal sweep efficiency. So another challenges could be the potential corrosion affecting the well and production facilities, as yet non-hydrocarbon gases must be separated from your sellable gas. So this is the some challenges in miscible gas injection. Then we should see the screening parameter for miscible project. So the typical parameter for a favorable miscible process, which I have put it down, has been defined in several publications. However, every field case should be studied individually considering all the factors inherent to that field, as your reservoir size, reserve, available fluids for injection are among the others. So we do have here gravity should be greater than 24 API, viscosity less than 10 cp, composition C1 to C7, oil saturation 30%, formation type your sandstone or carbon, net thickness, then average formation permeability, reservoir transmissibility, depth greater than 4000 feet, temperature, and other criteria. So these are the some screening parameter for your miscible project. So here we do have the average reservoir permeability. We will be taking as arithmetic or geometric weighted average of the permeability defined from the electrical law or your core used to populate a reservoir grid. So that could be, we can take this one. And then transmissibility is a term to express as a reservoir ability to move fluid as a function of your relative permeability, fluid viscosity, formation, volume factor, and geometric parameter. So now we come to the conclusion part. So what we understand in today's class, CO2 EOR ternary phase diagram. So what it is? It is a triangular graph used in petroleum engineering to describe how three component mix inside an oil reservoir used during your CO2 flooding. So three component, here we have the injectant gas, CO2 or other light gases, crude oil, that is hydrocarbon in reservoir, and then water and brine. So here we have the three vertex. So each corner or vertex of the triangle represents 100% of the one component. In ternary diagram, top vertex we can have a CO2, 100% CO2, then 100% oil and 100% water in the bottom left and right. Any point inside the triangle represents a mixture of these three components. So a ternary phase diagram usually contains your phase boundaries. So we do have the single phase, two phase and three phase region. So single phase region, all component mix into one fluid phase. Oil and gas will become miscible at the given thermodynamic condition, and this is ideal for your efficient oil recovery. So two phase region, fluid is split into two phases, CO2 rich phase and oil rich phase. So that is the least efficient displacement in this case. Then tie line we have seen inside the two phase region, lines called the tie lines, and that does connect your CO2 rich phase composition and oil rich phase composition. So they show how the fluid split after the equilibrium. So this two important miscibility mechanism occurs, that is vaporizing mechanism and condensing mechanism, and that is under your miscibility process. So vaporizing mechanism, light hydrocarbon vaporize into oil, into CO2, and condensing CO2 condenses into your oil phase. So this process eventually create the miscibility or dynamic miscibility, allowing CO2 to push oil more efficiently. So why this diagram becomes important, ternary phase diagram? It is being used to predict the miscibility condition, determine minimum miscibility pressure MMP, and design CO2 injection strategies, and to understand the phase behavior in the reservoir. So this is all for the today. See you in the next class. Thank you.